video, we're going to see a couple of examples to determine the projection of a vector or to find the component of a vector in a given direction. This direction may be an arbitrary direction, not necessarily to be x, y, or z direction. To find the projection of a vector in a given direction, we can use dot product. So in this case, we have a vector A and a given direction or a given line, we call it A line. We have a unit vector UA or UA hat to representing the direction of this line. Now the projection of a vector, we use A sub A. Okay, A means the vector, sub A means the direction it projects to. That projection equal to, or trigonometry, based on geometry, right? A equals to the magnitude A times cosine theta. But we can also get the same result by using dot product if the theta angle is not available. So the steps we're going to take will be, first, we need to find a unit vector UA hat along the line AA if it's not given. Second, we're going to perform dot product between the vector A and the unit vector UA. So be very careful with the operands of the dot product. So it's A and UA, unit vector of the direction, not any position vector along that direction, but it's the unit vector, which has a magnitude of 1. And this will give you the scalar projection because the dot product will give you, it's called a scalar product. So you have the magnitude of the projection. Example 1, we have a force acting on the hook at point A, and the force is given in vector form. And we have some dimensions given. We have point A, the hook is located at point A and with certain dimensions, and origin is O. We're looking for the angle between the force vector and the line AO, so which is the angle theta here. And we're also looking for the magnitude of the projection of the force along AO. So first of all, looking for the theta angle. To find the angle between two vectors, that's one application of the dot product. The dot product will give you, or two vector, now we have vector F and vector AO, right? F dot AO equals to the magnitude of F times the magnitude of AO times cosine theta. So if we can find vector AO, we can find the magnitude of AO, and we can find the magnitude of F, and we also already know the force vector in vector form. We can solve for theta angle. So an AO can be found, vector AO can be found because we already know point O is 0, 0, 0, and point A, we can find the coordinates based on the geometry. So that means we can use the dot product to find the angle between the two vectors, and then for the projection of the force along the line AO, if we can find cosine theta, the projection actually is just the force magnitude of force times cosine theta, or we can do F dot UA or UAO. Okay, so that means the first step is to find the position vector between the point A and O, which is RAO, and then we can find the angle, use inverse cosine of the dot product over the product of the magnitudes, and then we can find projection of the force using the dot product. Again, it's the dot F dot the unit vector of that direction, not the position vector in that direction. Or we can use F times cosine theta directly to find the projection. The answer will be the magnitude, which is a scalar. So with the plan, first let's find the position vector RAO. You can do imaginary walk since you have O at the origin. So from A to O, we'll do -2 as the z component, +2 the y component, and -1. So -2, +2, -1. So that's RAO. Again, the direction is from A to O, not O to A. So this is RAO, and meanwhile, you need to find the magnitude of RAO using the square root of sum of the squares. And F vector is given directly, so we can find the magnitude easily as well. From there, we can perform the dot product, and using the dot product to find the angle between the two vectors. Here is the dot product between F and RAO. And theta angle is the inverse dot product over the product of the magnitudes. And the angle is solved to be 57.67 degrees. And the last step is to find the projection of the force F along the line AO. So first, let's use the dot product between F and the unit vector AO. So that means we need to find the unit vector along the AO direction, UAO. So UAO equals to the position vector RAO divided by the magnitude of that position vector. And then we perform the dot product, force vector dot UAO. This will give us the projection of force along the AO direction. And dot product, again, keep in mind, will give us a scalar value. So your value will just be a number, 6 kilonewton. So that means the magnitude of the component in the AO direction of this force F is 6 kilonewton. We can also use geometry or trigonometry to find the value, which will be the magnitude of this force times cosine theta. So F times cosine theta will also give us this projection, or the component of the force along the AO direction. Since we already find cosine theta in the previous step, so let's double check using this method. Magnitude of F is 11.22 times cosine value, cosine theta, and the answer is also 6 kilonewton. Example 2. The given force acting on the pole at point A, shown here. Now we're looking for the components of the force acting parallel and perpendicular to the axis of the pole, which means we're looking for the component. One is parallel, means along this direction, AO direction, the direction of the pole, and another one is perpendicular to it. So this is the one way of asking this question, meaning you're going to resolve one force into two components. One component is along the given direction, and the another component is perpendicular to the given direction. If you think it in that way, or in this way, maybe it will be easier for us to understand. So here is the force F, and there's a given direction. So it's like to say that you're going to build a coordinate system from the tail of this force, and the given direction can be seen or can be treated as the x-axis, and you are going to find the y-axis, right, which is perpendicular to the x-axis. So this is x and that is y, and you're looking for the two components of this force, Fx and Fy, right? So Fx will be drop a perpendicular line to the x-axis. So this is our Fx, or that's the parallel component, okay? Because x-axis is the given direction now, and this component projection on it will be the component parallel to this axis. And of course, the other one will be the other component along the y direction, which is perpendicular to the x. This we will call it the perpendicular component. Okay, so again, if we're going to translate to what we're learning now, this parallel component is just the projection of the force in a given direction. In this case, this parallel is the component along the given OA direction. And the other component, the perpendicular one, is the one that perpendicular to OA direction. But from trigonometry, we know this perpendicular component equals to the magnitude of force squared minus this magnitude of the parallel squared, or the sum of the squares of this two components equal to the square of the original magnitude of the force, which is 600. Okay, so here are the steps. First, we need to find the force vector, the RAO, and UAO, because we're going to use F dot UAO to find the projection or the component of this force F along the given OA direction. After we find that projection along the given direction, we can find the perpendicular component by using the square root of the differences of the squares. First, let's figure out RAO and UAO. The position vector or the direction we need to figure out. So from AO, we can do an imaginary walk since it's a 3D, so it's easier and more clear if we do that. From A to O along the X, Y, Z direction. So along the Y direction is positive 4, along the X is negative 4, because we're traveling along the negative X direction, and Z direction is positive 2. So our OA will be negative 4I hat plus 4J hat plus 2K hat. The magnitude will be the square root of sum of the squares, and then we can find the unit vector, the direction of this OA, by using ROA divided by the magnitude of ROA. So divide each component by 6. So this is the result of this ROA. Next, we need to find the force vector F to perform the dot product between the F and the unit vector we just found here. We already solved this kind of problem earlier, right? When you have this projection plane of this force vector, to find the components, we can also do an imaginary walk to first identify those components on the diagram or on the figure, and then do the calculation later. So let's start from the tail of the vector and travel to the head. First, I will go along the y direction. So this is the Fy. and is a positive, then this will be the f of x. It will be a negative. So I'm putting negative sign here to remind myself. Then travel all the way up to the head of the vector in the positive z direction. Okay, and the next important information we want to specify on the 3D figure especially would be to specify the 90-degree angles. This darker blue triangle lying within the xy plane and x and y component are perpendicular to each other. And since this line is lying within the xy plane and the z direction is perpendicular to this plane, so it's perpendicular to any lines within this plane, includes the line I'm highlighting here. Okay, with those information, we can find those components easily, use trigonometry, right? So this side here, if we call that f prime, probably if we can identify that first, it will be easier for us to solve for fx and fy. So the length of f prime will be 600 times cosine 60 degree within the lighter blue triangle. And then we can figure out all the other components. The x component, again, as we said, is a negative scalar or negative component, is this f prime times sine 30. And y component is positive, is f prime times cosine 30. The z component will just be 600 times sine 60 in that lighter blue vertical triangle, and it's positive. So this is our force vector written in component format or vector format. So with two information given here, we have the force vector, we have the unit vector in the given direction. Then we can use the dot product to find the parallel component of force F or the projection of force F in the OA direction. It will just be the force vector dot UOA. And the result is positive here, 446 pound force. Keep in mind, it's not necessary to be always a positive value. It is a scalar value, but it can be positive or negative. It's just in this case, our answer is a positive value. And what is the magnitude of the force vector 600 pound force and the parallel component or the component along the OA direction, which is 446 pound force? We can easily find the perpendicular component of this force, which is calculated to be 401 pound force.